Vázquez, and I am here to present the paper Uncertainty-Aware Deep Learning for Robot Touch, Application to Bayesian Tactile Servo Control. So in this work, we propose the idea of using probabilistic deep learning approaches to the tactile robotics field. So the main source of inspirations come from two different fields. The first one is vision, which captures the underlying patterns of high-dimensional visual-based data. And then we have the probabilistic deep learning, which not only has the ability to generalize, but also to estimate and deal with uncertainty. These two fields have been applied to tactile robotics, which is a field that seeks to implement a human sense of touch in robots. So, in order to have a robust, reliable system, the robot must be able to adapt to uncertain and complex environments, to analyze and process high-dimensional data, and to generalize and isolate undesired effects coming from continuous tactile motion. For example, about the related work, there are some literature relating the use of deep learning with in optical tactile sensors that I will explain later, but I would like to focus on the uncertainty approach, in which we have been using a framework designed by Locarcio et al. Called a general framework for uncertainty estimation in deep learning. And this one uses two main techniques. The first one is calculating the data uncertainty coming from the sensors. In this one, it uses ADF networks, which have the ability to propagate the input sensor noise to the output. And then it calculates also the model uncertainty coming from training biases. So in this work, the author proposes to use the network with the dropout enabled, so that if you feed several times the same input, you will observe different outputs. So depending on the redundancy or the uncertainty over the predictions, it is possible to calculate this model uncertainty. About the platform we have been used, we used a normal personal computer, an ABB IRB 120 robotic arm with a tactile sensor mounted on it, and we have also used different 3D printed objects to test our results. About the software, we have been using Python and PyTorch for the deep learning part, OpenCV for post-processing some of the tactile images, and MATLAB. Okay, so what's the tactile sensor? So this is a 3D printed sensor that it is based on the optical tactile sensing technology. This sensor uses a deformable layer in which if you pay attention to the inside, you will see that it has several pins, so that when you apply pressure to the sensor, as you can see here in the image, all the pinout changes are deformed, so that if you use, for example, an inner camera and some deep learning algorithms, it is possible to infer how the sensor interacts with a surface or an edge only from the tactile images. About the system overview we propose in this work, it uses a closed-loop algorithm, and it is characterized by using an architecture with the ability to infer the pose estimation and its uncertainty coming from the tactile images. And then this information is used by a Kalman filter to predict in a better way the sensor pose. So then this information is fed into a closed-loop algorithm in order to maintain a fixed pose during the entire trajectory. So by doing so, it is possible to follow the contour of different shapes, as it can be seen here in the image. About the methodology followed, it was necessary to first train a deterministic ResNet, In this case, we had to gather a set of different tactile images, each one characterized by its x displacement, which corresponds to this one, and the dual rotation corresponding to this one. And we have also added unlabeled perturbances, in this case over the y displacement. And this has been done to generalize over the continuous tactile motion. About the uncertainty, it has been needed to tune different parameters of the uncertainty framework. The first one, coming from the ADF model, it was needed to characterize the noise of the sensors, and this has been set really low, as the images coming as tactile images are post-processed to segment the pinouts. And I would like to remind that for the model uncertainty, it is needed to use an architecture with the dropout enabled and to feed several times the same input. So to this end, the dropout has been set to guarantee the best quality estimation of the uncertainty. Then this information was the information related to the pose estimation and its uncertainty was fed into the Kalman filter that, along with the previous step prediction, it is possible to improve the performance. About the results achieved, first I would like to say that the deterministic architecture, the probabilistic ResNet, was able to achieve a similar performance to the one achieved by the deterministic architectures. And if we compare the probabilistic architectures and the Kalman filter, when using the Kalman filter, the error is reduced a lot, but the main difference can be seen in the mean squared error, and this is because the Kalman filter is quite good at rejecting the outliers predicted by the architecture. And about the online contour following, these are the results of the experiments with the robotic arm, and here we can see that the filtered approach was able to reduce the error of the trajectory and was able also to achieve a smoother trajectory as a consequence. And as expected, due to sampling-based methods to estimate the uncertainty, also the computational load was also increased. Here we can see other experiments in a teardrop and a clover. In both of them we can see that the smoothness parameter was also increased in both of them. And we can also see, for example, here in the clover, how the trajectory was also smoother when compared to the unfiltered approach. Okay, so what are the conclusions of this work? So first, this approach has proven a high decrease in the error by attenuating the effects of the outlier and by using temporal coherence via Kalman filter. Then the use of Bayesian approaches with uncertainty-aware feed-forward neural network presents as simpler and more accessible alternatives than other architectures, such as recurrent neural networks, that might present some drawbacks when training them. And as expected, the use of sampling-based methods to estimate the model uncertainty clearly increases the computational load of the overall system, which in some scenarios might compromise some real-time applications. Okay, and what's next? About the following steps, we have also considered two of them. The first one is to implement alternative filters to the Kalman filters to improve the pose estimation. And another one would be to take advantage of parallel computing to perform more efficient Monte Carlo sampling. Okay, and this is everything. Thank you for your attention. I would only like to add that I am currently looking for opportunities in the field of robotics and deep learning, for example. and it has been a pleasure. Thank you so much.